Alright, so in this video, we are going to be talking about an addition reaction, which is addition of a halogen and water to an alkene halohydrin. So we are taking this ring alkene and reacting it with Cl2, which is a halogen, and water to create additional halohydrin. Alright, visyl means groups that are on adjacent carbons, and halo as in a halogen, and hydrin as in a hydroxide group. Basically, we are going to be ending with the molecule that has a halogen and a hydroxide group that are on adjacent carbons. The first step of this reaction will be using the pi electrons to attack the Cl2. Don't forget the chlorines and draw out the lone pairs as well as the bond. So I'm drawing this arrow to show that the pi electrons are attacking the chlorine and the bonds between the two chlorines will break since they are relatively weak, thus creating a tertiary carbocation on one of the carbons and a chlorine bond. To complete this step, we need to decide to either conduct a carbocation rearrangement or draw out a resonance structure. If you look closely, there is a chlorine with lone pairs bonded to a carbon, and that carbon is bonded to a tertiary carbocation intermediate. Therefore, both groups are adjacent to each other. Therefore, we're going to be drawing a resonance structure. Whenever it comes to reactions like these, we are always going to be drawing out resonance structures since it is more stable than a carbocation rearrangement, and this reaction prefers it. Lastly, we need to draw out where the bonds are pointing. They're going to be pointing cis towards us and away from us, never trans, since that would create one of the bonds longer than it can be. Drawing out the chlorines with the lone pairs as well as the positive formal charge. And don't forget that because the bonds to the chlorine are pointing towards us, the methyl group has to be pointing away from us. Same for the other structure where the chlorine is pointing away from us and the methyl group is pointing towards us. In step 2 of this reaction, we will be introducing the second reactant, water, to act as a nucleophile to attack the electrophilic carbon. Adding H2O to both sides and the lone pairs onto the oxygen. Now that we know where the bonds are facing in the ring structure, that will dictate where the water attacks. So for the bonds facing towards us, the water will attack from the back side due to the front side being too stereoically hindered by the bonds. The same for the bonds facing away from us. The water will attack from the front side of the structure since the back side is too stereoically hindered by the bonds. This three-ring structure will break. The chlorine will go to the top where it was before, and the water will be now attached to the ring structure. All right, showing that the bond pointing away from us is the water and the bond pointing towards us is the chlorine. And similar for the structure on the bottom, where the bond pointing away from us is a chlorine and the bond pointing towards us is the water. Not forgetting the methyl group. Now moving on to our last step of this reaction, step 3, deprotonation. In this last step, we will be deprotonating with water, so the bonds on the oxygen will attach onto the hydrogen on the structure, deprotonating it, therefore creating a stable ring structure and a H3O group as products of the reaction. So drawing on the lone pairs onto the oxygen, I'm going to be drawing an arrow right here showing that the oxygen is going to bond to that hydrogen as well as for the structure on the bottom, therefore creating a deprotonated molecule. As I'm finishing drawing out the final products of this reaction, you will be able to see that it did turn out to be a vicinal halohydrin, like I mentioned in the beginning of the video, where vicinal meaning groups that are attached to adjacent carbon, and halohydrin as in halo meaning a halogen, and a hydrin as a hydroxide group. To wrap this reaction up, we need to look at the features of this reaction to see what it is about. We know from step 1 that the reaction is not able to do a carbocation rearrangement due to the reason that resonance is able to occur. So if there's an opportunity to conduct resonance, then that will trump the carbocation rearrangement in the reaction since it is more stable. Next, let's look at radioselectivity. One easy way to know if there is radioselectivity or not is if Marshall was introduced in the reaction, and no, it was not, so this product is not radioselective. Next, onto stereoselectivity. To find if the reaction is stereoselective or not, we need to use the 2 to the E rule. We count the chiral There are 3, so we plug that into the rule, and thus coming out with 6 possible stereoisomers, and we only created 2. So yes, the reaction is stereoselective. Lastly, let's look at the bonds. It will be an anti-addition since the bonds are trans to each other. So for the first molecule, the chlorine is pointing towards us and the hydroxide group is pointing away from us. And for the second molecule, the chlorine group is pointing away from us and the hydroxide group is pointing towards us, thus ending the reaction here.